If I told you that there was a time when the ocean was not the cradle of life, but a poisonous trap that killed everything, would you believe it? Throughout many stages of Earth's history, the oceans lost almost all of their oxygen, replaced instead by toxic hydrogen sulfide, turning the cradle of life into a deadly cauldron. We are used to thinking of the sea as the source of life, but there were times when it became a colossal killer. So, what made the ocean shift its role from nurturing mother to deadly assassin? And can we be certain that the sea will always remain a source of life, or will it one day become a destroyer once again? Watch until the end of this video to find the answer. Now, let us begin our journey in the Namib Desert, where the ghost ocean sleeps within black shales, waiting to be decoded. Part 1. The Haunting Ocean of the Past. A prologue from deep time. Did you know that one of Earth's most striking oceans is found in the middle of a barren desert? No more blue waves or colorful coral, only black shale glimmering with faint golden specks. That is pyrite. But pyrite is not just a pretty mineral, it is the trace of the ocean's past crime. Hundreds of millions of years ago, when seawater was stripped of oxygen, bacteria created toxic hydrogen sulfide gas. That pungent rotten egg smell bonded with iron, crystallizing into tiny grains of pyrite. They record one of the most catastrophic events in Earth's history, oceanic, anoxic events, OAEs. Imagine a vast sea, but instead of sparkling blue, suffocating black. These events were periods when huge swaths of the oceans lost their dissolved oxygen, turning them into toxic, sulfide-rich waters. Although they haven't occurred in millions of years, the geological record shows they happened repeatedly and may have contributed to several mass extinctions. How do we know these silent disasters occurred? Why answer lies in geochemical markers, much like finding fingerprints at a crime scene. When an ocean lacks oxygen, normal decomposition halts. Instead, organic matter sinks to the seafloor and is broken down by bacteria. In an oxygen-free environment, these microbes use sulfate section for respiration, releasing hydrogen sulfide, HAS, as a byproduct. Picture an entire ocean exhaling the stench of rotten eggs. This HAS then reacted with iron in sediments to form pyrite, FAC, a brassy gold mineral. The abundance of pyrite and organic carbon in black shale layers serve as a geological signature, proof of a global systemic collapse. Scientists today can observe a smaller-scale version of this phenomenon. Off the coast of Namibia, hydrogen sulfide eruptions occur when bacteria decompose dead marine life on the seafloor. When the toxic gas rises, it reacts with oxygen, forming white sulfur particles that turn seawater into a surreal, bright green haze, beautiful but deadly. This striking imagery not only revives scenes from the ancient past, but also reveals the deadly hues that once cloaked the primordial oceans. The first breath of the planet, a history of paradox. Here's a surprising fact. Billions of years ago, Earth's oceans were naturally oxygen-poor and rich in hardias. They were dark purple-black, dense and stagnant, unfit for complex life. This chemical state is thought to have delayed the rise of multicellular organisms. Then, about 2.4 billion years ago, a monumental turning point occurred, the Great Oxidation Event, GOE, driven by the photosynthesis of cyanobacteria. This process transformed Earth, dramatically increasing oxygen levels in the atmosphere and oceans. Geological evidence of this shift includes the emergence of red beds, of sandstone, and the disappearance of banded iron formations like the planet had put on a new coat of color. After billions of years of evolution in an oxygen-rich world, life became dependent on it. Thus, the real disaster was not the arrival of anoxic conditions, but their return. What was once the normal state of an ancient world became an apocalypse for complex life. Instead of a mere environmental shift, it was a sudden reversion to a primitive state, a deadly door opening to threaten every organism accustomed to breathing clean ocean air. Part 2. A planet holding its breath. Tipping points and great deaths. The engine of destruction, volcanism and warming. The primary driver behind the most extreme oceanic anoxic events were massive volcanic eruptions, such as the Siberian traps at the end of the Permian. Picture volcanoes erupting like thousands of colossal smokestacks, pumping out enormous amounts of carbon dioxide, CO, into the atmosphere. The result, Earth heated like a giant furnace, with global temperatures possibly exceeding 25 degrees C. Warm water, like a shaken soda, holds less oxygen. Worse yet, the temperature gap between surface waters and the deep created layers, like a heavy blanket smothering the ocean, blocking oxygen from reaching the depths. This stratification acted as a lid. At the same time, an accelerated hydrological cycle washed in vast amounts of nutrients, like nitrates and phosphates, fueling algal blooms. The blue sea turned into a green soup. When the algae died and sank, their decomposition consumed what little oxygen remained. The death loop began, an autopilot feedback machine powered by suffocation. Toxins. Rising to the sky, the Kump hypothesis. The rise of HUS in the oceans led to an even more nightmarish scenario called the Kump hypothesis. Once HUS concentrations in deep waters surpassed a threshold, the boundary between them and oxygen-rich surface layers, the chemocline, suddenly rose. When that veil tore open, toxic HAS escaped directly into the atmosphere. Think of it as a double-edged weapon. First, HUS poisoned plants and animals on land. But the deadlier blow was its potential destruction of the ozone layer, Earth's sunshade. With that shield stripped, the planet was laid bare to lethal ultraviolet radiation from the sun. Evidence of this catastrophe is seen in fossil spores from the Permian-Triassic boundary, scarred and deformed as if burned by UV rays. No wonder this event wiped out a third of insect species and over two-thirds of reptiles and amphibians. A double blow, the ocean died, then poisoned the air, stripping away the planet's final armor. Imagine opening your window one morning, not to fresh air, but to the choking stench of rotten eggs. Yes, that was Earth's house cleaning, 252 million years ago. The first victims, the late Devonian extinction. Before the end, Permian cataclysm, another disaster struck 100 million years earlier. The Devonian was known as the Age of Fishes, a bustling underwater metropolis teeming with diversity. At the top of the food chain were placoderms, the first jawed fish, clad in bony armor like steel warriors. The true ruler of the seas was Dunkley osteus, a monster, nearly 9 meters long, weighing 4 tons. Modern studies revise its size to about 3.44.1 meters, but its power remains terrifying. Its jaws acted like steel guillotines, generating a bite force of 7,400 newtons, enough to slice through armored prey. The Devonian seas were also decorated with colossal coral skyscrapers. Reef systems built by tabulate corals, rugose corals, and stromatoporoid sponges reached thicknesses of over 1,000 meters and span hundreds of square kilometers, greater than today's Great Barrier Reef. But then, the late Devonian extinction struck, bringing anoxia and global climate disruption. The placoderms vanished entirely, and the super reefs disappeared from the map of life. Part 3. Great Deaths and the Long Road to Renewal. The end Permian extinction marked the climax of anoxic disasters, erasing an estimated 96% of marine species. It was the final chapter for many dominant Paleozoic groups. Trilobites, one of Earth's earliest and most successful animal lineages, could not survive this storm. Imagine a dynasty that ruled the seas for 270 million years, snuffed out like a candle in a hurricane. Though they had endured earlier crises, they never regained diversity and vanished completely by the end of the Permian. Some trilobites, like Olenidae, even formed symbiotic relationships with sulfur-eating bacteria, enabling survival in sulfide-rich, oxygen-poor waters. They developed wide thoraxes to host the bacteria and degenerated eyes for dark environments, as if outsourcing their lives to microscopic tenants. But these specializations were no match against a multi-pronged catastrophe of anoxia, ocean acidification, global warming, and UV radiation. This wasn't a single storm, but a perfect storm, from all sides. Survival under one stressor could not guarantee survival against the full onslaught. Other spectacular creatures like sea scorpions, eurypterids, giant arthropods reaching 2.5 meters also vanished entirely. Picture a massive scorpion crawling in shallow seas, now only remembered in fossils. Likewise, the great coral builders of the Devonian rugose and tabulate corals were wiped out, leaving behind an ecological void lasting millions of years. Recovery after a mass extinction was never quick. It could take millions of years, far longer than the extinction itself. During this time, Earth systems repaired themselves, and new life forms evolved to fill the empty niches. Like a city after war, ruins fell in days, but rebuilding took decades, even centuries. For example, after the placoderms disappeared, bony fishes, osteichthyes, rapidly diversified and became the dominant vertebrates. Opportunistic seat fillers, they claimed the throne of the seas. Similarly, the vast Devonian reefs were erased, but eventually, a new coral empire arose. Modern reefs are not built by Paleozoic corals, but by scleractinian corals. They appear in the fossil record 10 to 14 million years after the Permian extinction. Crucially, these corals evolved a new survival strategy, a symbiosis with photosynthetic algae called zooxanthellae. Paleozoic corals may have lacked this partnership, leaving them vulnerable. Think corals are passive? Think again. They had a secret pet, algae that captured sunlight. Like a grandma keeping a cat, but instead harvesting solar energy. The new world was not a replica of the old. It was a biological reboot, built on fresh strategies and innovations. To grasp this rebirth, compare two marvels. The ancient Devonian reefs, though destroyed, testify to colossal life reef walls towering a kilometer under the sea. But the Great Barrier Reef, Earth's largest living structure, only began forming about 1,000 years ago after the last ice age. Spanning 8,000 km, larger than the UK, it is so vast it glows as a bright scar visible from space. This shows that after catastrophe, life does rebound, often with new complexity and scale, but only after immense stretches of geological time. The ancient story replayed our modern reality. Earth's past has a chilling parallel today. Modern ocean dead zones are regions where oxygen levels are too low to sustain most marine life. They are not isolated accidents, but a global phenomenon spreading rapidly. For instance, the Gulf of Mexico dead zone can reach over 8,000 square miles, about 2.8 million acres every year. It is like a vast underwater graveyard where fish and crabs vanish, leaving only bacteria. Coastal dead zones have increased tenfold in the last 50 years. The main culprit caused by humans is nutrient pollution, primarily from agricultural runoff and sewage. This is the modern version of ancient volcanic fallout. If volcanic ash was the spice of death back then, today fertilizer and pesticides play the same role. Nutrient overload triggers algal blooms. When they die and sink, microbes decompose them, depleting oxygen and creating dead zones. Worse, climate change amplifies the crisis. Warmer water naturally holds less oxygen. Climate models also show increased rainfall will wash more nutrients into coasts. A hotter, wetter Earth is stoking the fire. Together, these drivers reinforce stratification and accelerate oxygen loss, replicating the same dynamics behind ancient anoxic events. The difference is, this time, the experiment is unfolding within a single human lifetime. We are recreating a global trial that once nearly wiped out complex life. In the past, giant volcanic eruptions cooked oceans, releasing billions of tons of CO2 and suffocating marine life. But in the 21st century, the culprit is no longer volcanoes, it is us. From fertilizers pouring into rivers to untreated sewage flowing into the sea, all act as mini cow-eye pipes and global nutrient spreaders. The result, swollen dead zones, vanishing oxygen, algal blooms, and death spirals, eerily similar to the triggers of ancient extinctions. The story of Earth's deep past is not just scientific curiosity, it is a handbook for our present. Ancient anoxic events were runaway planetary feedback loops triggered by external forces. Today, we are that external force. The black shales of the Permian and the dead zones of the Gulf of Mexico both testify to the same fundamental system failure. Our ability to read these past warning signs may be our only hope to avoid repeating history. The ocean was once the cradle of life, but also its grave. When the planet lost balance, the sea turned into a killing machine, exhaling toxins and erasing nearly all creatures. So, will the ocean always remain gentle? History says no. And more frightening, today the recipe for destruction comes not from ancient volcanoes, but from human hands. Pollution, climate, spreading dead zones. Lesson could not be clearer. Life endures not through brute strength, but through adaptability and change. The black shales of the past do not only tell stories of what was, but mirror what may come. So, as we face suffocating seas today, the question is not whether the ocean will destroy us, but whether we have the wisdom and will to change before it's too late. And you? What do you think humanity should learn most from the past? Strength, adaptability, or evolution's creativity? Share your thoughts below. And if you found this story meaningful, don't forget to like, share, and subscribe to join us in the next journeys uncovering Earth's hidden secrets.